In this last video for Chapter 4, we're going to look at the three key examples for mechanical vibrations, which are called undamped, critically damped, and underdamped. So we're going to look at the undamped case first. That would be where we have a differential equation. Remember, the differential equation framework for a damped system was my double prime plus by prime plus ky equals 0. In this case 1, we're going to assume that b equals 0, so we have my double prime plus ky equals 0, and we're going to rewrite that as y double prime plus omega y equals 0. As omega squared, so it's easier to solve. So the characteristic equation for that is going to be r squared plus omega equals 0, or r equals plus or minus omega I, or we get the solution y equals c1 cosine omega t plus c2 sine omega t. Now we're going to want to rewrite that solution in a different form so that it's easier to work with and easier to determine where the solution curve is going. So let's move that solution form to the next blackboard and write it in a different structure. That new structure that we want to use is going to be y equals a sine omega t plus phi. And if we use the sum rule for the sine function and expand that, we get sine omega t cosine phi plus cosine omega t sine of phi. And so if we let cosine omega t equals c1 and sine omega phi equals c2, or sine phi equals c2, then we are back to where we were before. So if we take that information and put sine of phi over cosine of phi, which is tangent of phi, we see that is c1 over c2, and so that is one of our requirements, that the c1 over c2 is related to phi in this way. The other requirement is that there is a mistake here. I need to fix this. C1 needs to equal a times cosine of phi, and the C2 needs to equal a times sine of phi, or we're not going to be able to transform this version of the solution into this form of the solution. So that means that if we square C1 plus C2, that gives us a squared times cosine squared phi times plus sine squared phi. And so the other requirement that we're going to need here is that if we take the square root of both sides of that, we see that c1 squared plus c2 squared equals a. So from now on, we're going to use this form of the solution in the undamped case, and the way we get from this form right here to this form right here is to have c1 squared plus c2 squared equal a. that's the C1 and C2 from the original, from this form of the solution, right? So we have to get this form of the solution first to get A, and then we calculate the phi as tangent inverse of C1 over C2. So let's see how we actually do that in an example problem. So in this problem we have a 1/8 kilogram mass, that would be 1/8 y double prime, and it is attached to a spring of stiffness 16, so that would be plus 16y equals 0. So that is our initial differential equation. There is no damping force, so there is no y prime term. Also have this given information, y of 0 is initially 1/2. In words, the mass is initially displaced 1/2 meter to the right of equilibrium, and it has an outward velocity of square root of 2 meters per second. That's y prime of 0 equals square root of 2. So let's solve this differential equation on the next blackboard. So the differential equation can be rewritten as y double prime plus 128 y equals 0. Characteristic is r squared plus 128 equals 0. R equals plus or minus square root of 128i, which is plus or minus, that's 64 times 2, so that's 8 square roots of 2i. So the solution is C1 cosine 8 square roots of 2i plus C2 sine 8 square roots of 2i. Excuse me, that's C1 cosine 8 square roots of 2 t plus C2 sine 8 square roots of 2t. So now we're going to calculate phi and a. Remember that a equals the square root of C1 squared plus C2 squared, and phi equals tangent inverse of C1 over C2, so we need to find C1 and C2. So y of 0 is 2, but if we plug 0 in for t here and here, we just get C1 on the right side, so that gives us that C1 equals 2. Now y prime of 0 is given to be the square root of 2, so y prime of 0 square root of 2, but what is y prime of 0? It is minus 8 square roots of 2 C1 sine 8 square roots of 2t plus 8 square roots of 2 C2 cosine 8 square roots of 2t. And if we plug 0 into that for t here and here, we get that this term, this entire term equals 0, so the right side is 8 square roots of 2 C2. 8 square roots of 2 C2 is equal to the square root of 2, and so C2 is equal to 1/8. And so C2 is 1/8, and C1 is 2. So A is C1 squared plus C2 squared, which is 4 plus 1/8, or 2 squared plus 1/8 squared, which is 4 plus 1 over 64. There's an error here. Y of 0 was given to be 1/2, so C1 is 1/2. So let's fix A. So A is 1/2 squared plus 1/8 squared, which is a fourth, plus a 64th, which is 8, or actually 16 plus 1 over 64. So A is square root of 17 over 4. What about phi? So phi is tangent inverse of C1, which is a half, over C2, which is an eighth. Tangent inverse of 4, and tangent inverse of 4 is 1.36. The way we determine the quadrant in which phi lies is by looking at the sign of C1 and C2. So if both of those are plus, it's in quadrant 1. If C1 is negative and C2 is positive, it's in quadrant 2. If both are negative, quadrant 3. And if C1 is positive and C2 is negative, quadrant 4. So this is C1, this is C2. So both of our C1 and C2 values were positive, so the tangent inverse is in quadrant 1. So now we have our solution expressible in this other form. The amplitude A, the square root of 17 over 4, sine omega was 8, square roots of 2t plus phi was 1.36. When does this return to equilibrium? Well, that's when this solution equals 0. The sign equals 0 whenever the angle that we put in, 8 square roots of t, or 8 square root of 2t plus 1.36 is a multiple of pi. And the first multiple of pi would be when n equals 1. And so if we solve for that, we get t equals pi minus 1.36 divided by 8 square roots of 2, and that is approximately 0.16 seconds. So we've just found that in the undamped case, the solution looks like this, and that we can determine when it first returns equilibrium, as we just did. So our case 2 is going to be when we are overdamped let's look at the underdamped case first. So here we have m y double prime plus b y prime plus ky equals 0. It's the case when b squared minus 4ac is negative, or actually b squared, in this case minus 4mk, is negative, and we get the solution that looks like this: c1 e to the alpha t c1 cosine omega t plus c2 sine omega t. And it turns out that we can turn this into a more desirable structure: a e to the alpha t sine omega t plus phi, just like before, where the A equals square root of C1 squared plus C2 squared, and the phi is tangent inverse of C1 over C2 with the quadrant of phi determined by the sines of C1 and C2. So let's use this structure right here and solve an underdamped case problem on the next blackboard. Right, so it's oscillating but constrained above and below by the decaying exponential function. So in this second, so if we have this differential equation, y double prime plus by prime plus 25y equals 0, and y of 0 is 1, and y prime of 0 is 0, then if b equals 6, then b squared minus 4ac is negative, so that would be an underdamped case. So let's solve that. So negative 6 plus or minus square root of 36 minus 100 over 2 gives us minus 3 plus or minus 4i. So y equals e to the minus 3t c1 cosine 4t plus c2 sine of 4t. Now we need to find those constants. C1 and C2, we're given that y of 0 is 1. And if we plug that in, that tells us that C1 equals 1. Y prime of 0 takes a little bit of work, right? It is minus 3e to the minus 3t C1 cosine 4t plus C2 sine 4t, and then e to the minus 3t times minus 4c1 sine 4t and plus 4c2 cosine 4t. And we're plugging 0 in, which gives us a non-zero term here with the cosine and the cosine here. So that's what, minus 3c1 plus 4c2 equals 0. Plugging in 1 for c1 gives us c2 is 3/4. So c1 was 1 and c2 was 3/4. A equals the square root of 1 squared plus 9/16, which is the square root of 25/16, which is 5/4, and phi is tangent inverse of 1 divided by 3/4, which is tangent inverse of 4/3, which is 0.9273, and it's in quadrant 1 because both C1 and C2 are positive, so we get this alternate form of the solution, y equals 5/4. So here's our solution in this alternate form. which we can then use to solve for when the mass first returns to equilibrium, or when it has a max or a min. Let's do one final example of a so we've done no damping, underdamped. Let's do now what is called critically damped. So remember, our differential equation was y double prime plus by prime plus 25y equals 0. Y of 0 is 1, and y prime of 0 was 0. And if we let b equal 10, then the characteristic equation is r squared plus 10r plus 25 equals 0, or minus 10 plus or minus square root of 100 minus 100. So critically damped is when b squared minus 4ac equals 0. So the root is minus 5 repeated, and the solution is c1e to the minus 5t plus c2t e to the minus 5t. So solving for c1 and c2, y of 0 is just c1, which is 1, and so we have that solution, or the value of c1 right away. And c2 takes a little bit more work, so y equals c1 e to the minus 5t plus c2t e to the minus 5t, y prime minus 5c1 e to the minus 5t, and then the parts or product rule here, so c2 e to the minus 5t for derivative first times second, plus, or actually minus 5 c2t e to the minus 5t. So y prime of 0 would be what? Minus 5 c1 plus c2 plus 0 equals 0. Remember that our c1 was 1, so minus 5 plus c2 equals 0, c2 equals 5. And so putting that all together, y equals c1 e to the minus 5t plus c2t e to the minus 5t. We get our solution as e to the minus 5t plus 5t e to the minus 5t. And in this critically damped case, we don't have to go through the complications of finding the a and the phi, because it's not a batch structure. So this is the critically damped case. And just one more picture. When we have over damped or critically damped, what do those solutions look like? They are either going to go to equilibrium like this, or they're going to go to a max and go to equilibrium. Excuse me, I didn't say that right. They're going to, they never actually hit equilibrium, because there are these kinds of exponential functions. If they're critically damped, right, they're never going to hit 0. So they may just stay always above, or they may have a max and then stay above, or they may drop to a min and stay below. Let's just do a quick recap here. The solutions that we get if we have underdamped, or no damping, excuse me, would be C1 cosine omega t plus C2 sine omega t, solutions that just keep oscillating back and forth because there's no damping or friction. In this case, we generally want to rewrite them in this form: a sine omega t plus phi, where a equals square root of c1 squared plus c2 squared, and phi equals tangent inverse of c1 over c2. In the underdamped case, so think of this as the shock absorber is not quite working as well as it should, and so while you'd like to return to equilibrium quickly, it takes a little longer to do that. These differential equations are exponentials with alpha negative, so they're decaying exponentials times sine and cosine. Decaying exponential constrains it, top and bottom, and the sine and cosine makes it oscillate. Again, we want to rewrite this in a form where it's easier to find what's happening to the differential equation, and that form is very similar to the case that we looked at before. Structurally very similar, where C or A is the square root of c1 squared plus c2 squared, and phi is tan inverse of c1 over c2. And then our final case, which is the critically damped. In the picture, this is the case where it returns to, well, it won't return to equilibrium, so it either stays above or has a max and stays above, or has a min and stays above. These look like y equals c1 e to the rt plus c2t e to the rt. The root is repeated, and the only thing we need to do in this case is find the c1 and c2. We don't need to put it into an alternate form. So this concludes this video on mass spring systems, where we've taken a look at the three types of examples: the undamped, the underdamped, and the critically damped.